So for the workshop, if you want to follow along, I have a small notebook, and you can find it here. Okay, so if you download this Pluto notebook and you run it on your computer, there is a small exercise at the end, and you can do the exercise. I've tried last minute adding the QR code in my slides, but now it's compiling. Okay, so today I'm going to talk about JuMP. So what is JuMP? We have a nice website when you can find a lot of information about this. So it's a large project with many people involved. So you can find more information here about all the contributors to JuMP and all the managers to the many different packages in the ecosystem. So I'm going to represent the work of many people, and I'm going to try in this tutorial to make it very introductory and start from scratch. And suppose you don't know anything about JuMP. Okay, if later you want to find more information, we have a nice documentation with many tutorials and examples that you can find. And we also have a JuMP dev workshop in New Zealand soon in November. That is close to CPAIOR, which is in Australia. So if you want to join us in New Zealand to talk, we'll talk a lot about JuMP, and there are many nice talks that are planned. Okay. So how does it work with JuMP? So the first thing you need to know is you need to create a model. And when you create a model, you can specify the solver, but you don't need to specify it when you create the model. It can be specified later. So in this case, we are going to use HAS. If you want to find the list of all the possible solver, we have a list here. We have a long table, which is probably not exhaustive, but many solvers that we know about are in this table. And one thing that's important to look at in this table is this column. This is the class of problem that the solver is able to solve. Okay, so there is the nonlinear programming class. For this class of solvers, what we are going to give to the solver is an oracle for the solver to get the gradient or the Hessian vector product at a given point. Then you have linear programming solvers. These only work if all your constraints are linear. And then you have the conic solvers, which support nonlinear constraints, but that need to be encoded in a very specific form. So they need to be encoded in a form where this is a linear expression that belongs to some cones, which is called the conic form. If you write the problem in the nonlinear way, that's not necessarily in the conic form, then you need to either write the conic form yourself, or you can use convex.jl. In convex.jl, you can write your solver in a nonlinear way, and it's going to try to write the conic form for you. Okay. But at the moment in JuMP, we expect you, if you want to use a conic solver, to write the conic form explicitly. Okay. And so in this case, okay, so my QR code didn't work. So if you want, I think it's easier to just write this in your browser and then click on talks, and this is this one. Okay. All right, so the whole idea of JuMP is that we try to, there are many different solvers as you see, but we try to make it very easy to write a model mathematically, so that when you read your model, it really looks like the LaTeX version if you want. So you can very easily verify that the model is mathematically exactly what you want. And then you can try one solver and then try a different solver, and you don't need to change anything in your model to swap the solvers. They should just solve very differently the same model. So you know that, in a sense, they should normally find the same solution if there's only one optimal solution, but probably with a different speed. Okay, that's really what we want to allow you to do is only think about, is my model mathematically correct? Does it correspond to what I want? And then I can just try many different solvers of the list. And to change the solver, you should just, of course, there is only one solver you can set at creation, but you can also use set optimizer after, and then you can change the solver and then re-optimize and see what's the difference. Okay, but this is a nice goal, but of course, if we want the model to be understandable by all solvers, maybe it's a bad idea, because maybe there are some solvers that support very specialized constraints that other solvers don't support. So if we have the goal to have the same model used by all solvers, it may prevent you to use solver-specific features. Okay, so in JuMP, we didn't want that, so we tried very hard to have the same model work for all solvers, but still be able to use some specific, to be able to transmit to solvers specific information about the solver that this solver will be able to exploit, but all solvers won't be able to exploit. Okay, so normally, if in your model you write some specific feature that some solvers support, for the other ones we are just going to rewrite them. Okay, so that's really the goal. We want to be able for you to write the same model for all solvers, but still be able to use the solver-specific features to get the best performance of the solver, the same performance you would get if you just write a model hard-coded for that solver. Okay, so how do you write this model? So the first concept that I need to introduce is the concept of a decision variable that is common for you if you already done optimization. So in JuMP, you define the decision variable with the add variable macro. Okay, and the add variable macro takes a model, the model you're building, and then it takes the name of the variable. And if you want to add bounds to the variable, now is the time. You can also do it later, but this will be the most readable to write it like this. And you can also create containers of variable. Okay, and containers in JuMP, we want to abstract away what is the container that's going to be created. So if here you write I that goes from 1 to 3, then what is going to be created is basically a normal Julia vector. So it's a classical Julia vector, but that contains JuMP variable. If the container, for example, starts from 0, then we cannot use a normal Julia vector. I have already a Z in this notebook. Then what we create is something we define inside JuMP, which is a dense axis array, which is the same, which is basically like a vector, but where the axis is not from 1 to 3, or from 1 to n. So you cannot index it as a vector. And if you add a condition, for example, I want that only take the case where I is odd. Or for example, I want to say I from 0 to 3 and then j from 1 to I. So basically the second dimension depends on the first one. So it's not going to be a rectangular array. Let's call it AA. I'm sure I haven't used AA yet. And then we use a sparse axis array. Okay. So a question that comes often is why do we have to define our own containers, and why don't we use something that already exists in Julia? There are already many containers that exist. The reason is that we want for the user that this detail is never important for them to understand. So in a sense, they have these arrays, have these indices, and we want the sparse axis array and the dense axis array to behave exactly with the same interface as the normal arrays. And if you look at other extension of arrays, then essentially when you need to index with the custom indices, you have a different syntax. And so you need to know that you're not using arrays. We want the user to just not have to know that suddenly different arrays are used. It's exactly the same interface. Okay. So we somehow have to define these arrays, which are direct generalization of the normal arrays. And we've never found any other equivalent in Julia at the moment. Okay, so here Y had disappeared. So maybe I can sum A. And then you have the concept of optimization objective function. So when you ask the solver to optimize the problem, what you're essentially asking is to find the value of this decision variable that minimize some function. So here, I want to minimize 12 times x plus 20 times the sum of the elements of AA. And so this one takes the model, whether you minimize or maximize, and then the objective. So normally the objective is just one scalar function. There are some solvers that support multi-objective. So then you have basically a Pareto frontier of optimal solution. This is a feature that we added recently. In that case, you would add a vector of all the objective. Okay. And we have now some solvers that support that. So again, my Y has disappeared. Let's go back to my Y. So when you use Pluto with JuMP, they don't understand each other exactly. Like JuMP doesn't completely satisfy all the assumptions of Pluto. But you can still work around it. It's just sometimes you need to just redefine your model, and then it works. Okay. Because JuMP will never allow you to create twice a variable with the same name, and then Pluto has other constraints. But you can work around it. Okay, so how do constraints work? It's again 3 arguments. First the model, then the constraints name, and then the actual constraints. And so you write it a bit like you would write in math or in LaTeX. Here it's 6 times x plus 8 times the vector y minus y2 greater than 100. This means that I'm only going to consider solutions that satisfy these constraints. Okay, so once you define the constraints, the problem is completely described. This means I want to find the value of x and y that minimize this objective among all the solutions that satisfy these constraints. I don't strictly have to define a name for these constraints. The name can be used for printing, but they are also used to easily access the dual variables. So you could not give name and then access the dual variables, but then if you see the dual variables of the 2 inequality constraints, you want to be sure of which dual correspond to this one and which dual correspond to this one. So the easiest way to do this is when you create the constraint, you give them names. And then later, when you will want to access the dual, you can directly ask, I'm the dual of this constraint. Okay. Another important point is why is this model we always give. We are always going to check that when you give variables in the constraints, these variables belong to the same model. This is because many bugs can occur when you actually manipulate different models, especially with a notebook. Then maybe you create a new model and you use the variable of the old model. By checking that you don't give us variable of another model, you catch a lot of bugs like that. And so we always check that. Okay, once you've created the model, there are 2 ways to print it. There is the very summarized way. Like this, you can see, okay, that's my solver. It doesn't have an objective. It should have an objective. I know that's because I need to reevaluate it. Okay. it has an objective, it has 4 variables, 11 constraints, and they are name registered in the model. The registered name in the model are very useful. So suppose that you create your model and then you have some other functions, or the Julia function that takes the model as argument and needs to take the dual of C1, for example. Well, C1 is a Julia variable, C2 as well. So in this context, they are in the scope, you can access them. But if you only give to a function the model, you don't want to also have to pass along this Julia variable, the Y Julia variable, the C1 Julia variable, and the C2 Julia variable. Especially when you create a large model and there are many different places in the source code that add things to the model, you don't want to have to keep track of also all these. So basically what we have in JuMP is we simply have a dictionary that maps the names registered with the actual Julia variable. So if you want to recover C1, you can just get it back. And you have the constraint back. And this should be exactly the same as C1. Okay. And so that's very useful when you start having a larger project and you need to manipulate a model. This is what's going to make your code a lot simpler and more maintainable. You can also print the model, and then you have all information. You have the variable bounds that are written like this, and the constraints. Okay. Now we actually have not done any optimization yet. So we just have created the model. So we could have not even given the solver. That's fine. You can not specify the solver, build the whole model, and then only give the solver later. In this case, we have already given the solver, so we can just solve. So we can hit optimize. And then we are going to do many things internally to prepare the solver exactly in the format that Hayes wants. And then we give it to Hayes, and it's going to solve this linear program and then give me the solution. What's very important here, so here it's going to print me the log. This is very useful. For example, if you solve a big problem, then you don't have your computer that seems frozen for a while. You see that, okay, it's iterating, it gives me some updates once in a while. I see the progress it's making. You can see whether it's making a lot of progress or whether it is making not a lot of progress. And so we have the convention that every solver by default should have the log enabled. But of course, if you write a package using JuMP many times as some kind of sub-problem, you don't want the user to see many small logs appearing all the time. And so you want to say to the solver, you're just solving small problems, so don't say anything. And so you can use set silent to say silent the solver. Okay. And this is going through the system of attributes that we have in JuMP. So attributes is one way that we've tried to make JuMP easy to extend, and also to be able to basically communicate specific features for the solver, even if the model itself is solver independent. And so solvers can define custom attributes. And these custom attributes are basically the way that you specify the tolerance, the maximum number of iterations, and all the things like that. Okay. And this is the concept of attributes in JuMP is a very extensible concept, and that's or many of the extension are able to work, because behind JuMP, the way we work is we have the solver interface called matopt interface. And if you want to define transformation to the problem or something like that, you can define a matopt interface layers. And so behind JuMP, you have a stack of layers before the solvers. And basically, because if the solvers define new attributes, then for each layers, they will just see custom attributes and they know what to do with them. If they didn't define this attribute, they can just pass it along down the stack. And so it's very easy to define custom attributes and make it work with all the extensions and so on. So that's an important concept, but here silent, even if it's one attribute, because it's so useful, we make it a custom JuMP function to make the interface very, very simple and clear.
Is there a way to get a list of attributes that support
we don't have the list of attributes supported by a solver. What we do is that we ask the solver to write it in their README. And so you can check the README of the solver and they should say what are the custom attributes. So if you have try to standardize the README of all solvers, so that they should say in the README what are the supported constraints, what are the supported attributes. But you cannot ask for the list of the supported constraints. But you can check if a specific constraint is supported or not, or attribute is supported or not. Good question. Okay, so when you fetch the result, there is some very important things to consider. JuMP will not tell you anything if the solving process failed. And the reason for that is that we, even if we want JuMP to have a nice, readable, user-facing interface, we want it to be suitable to be a building block of a larger Julia package. Okay, so larger Julia package could just use JuMP as some low-level tools. And from that perspective, we need to give the user full control over what's happening. And so in a sense, even if you can just use it in some script where it makes sense that it should actually throw an error or a warning if the solve failed, we don't do this, okay? But we try to warn the user enough to let you know that you should always, when you solve, check what's the quality of the solution. Okay, and so there is the solution summary, which gives you all the things you should, all the basically information you should be looking for. So what's the termination status is why the solver stopped. And then you have the primal and dual status, which are what is the status of the solution of the primal and the dual. So in the design of the solver interface, we try to fit many use cases. So you can actually have several solutions. Many solvers return just one solution, but some return several solutions. So we have the concept of multiple solutions. And for each solution, you can have a primal and a dual solution. And for the primal and the dual solution, you can ask for this solution, what is the status of the primal and the dual? And the status can be, this is a feasible solution, this is an infeasible solution, this is a certificate that the other side is infeasible. So the primal could say the dual is infeasible, the dual could be a certificate that the primal is infeasible. That's the status of the solution. And then the termination status is basically why the solver stopped. And so if you want to, so usually in optimization, we like to just give one status, but we actually split it in three because it's much clearer like that. And a very important case that used to be confusing for older version of JuMP is when a problem is unbounded. Because when a problem is unbounded, the thing is you actually don't get a proof on unboundedness. What you get is a primal solution that is a proof that the dual is infeasible. But the fact that the dual is infeasible doesn't mean that you're unbounded. It just means that there is a ray that you can follow to increase the objective function infinitely, but you still need to have at least one feasible solution as well. If you have one feasible solution in an array, then you can have solution as large as you want. And usually, actually, you only have a proof that the dual is infeasible, and then you can resolve with a zero objective, for instance, and then you can get a feasible solution, and then you have a full certificate of unboundedness. So that's why we actually don't have an unbounded status. We have dual infeasible. Okay. So in a sense, this is very flexible in the sense that we should be able to represent many cases, but you should combine the different information to get the actual understanding of, okay, what's the status of this. Okay, so I think I should rerun my cells. Yeah, okay. And so in here, you can get the value of a variable, the value of the dual of a constraint. And here, because C2 actually contains a vector of constraint, you can broadcast dual to get the value of all of them. Okay. So here, if you want to, so usually you want to programmatically check these things. So the solution summary is nice if a human wants to get a sense of what's the solution. If you want to programmatically check with if else what's the status, you can ask what's the termination status and so on, which is exactly, these are exactly the name of the JuMP function you should use to get these values. Okay. And these three, they are actually enums, so Julia enums. And the reason they are enums is that with enums, it's very easy for you to do if else and check all the cases. But then it's restrictive for the solver to give you what's the status. And so we also have the row status, which is an arbitrary string. And so if the solver feels restricted with these three enums, and he wants to say something custom, he can just return any string here. Okay, so this one is not good for if else, but it's good for humans. Okay, so now we come to an example. So we are going to do an AC optimal power flow example. So what, and we'll have a small exercise when you need to find how to build a constraint. And then we'll discuss what are the important considerations when you think about different ways to formulate the constraints. And this will go into a bit more the inner working of JuMP, which are important to understand the performances. Okay, so this is the problem. So what you have is you have 3 generators. You have 4 nodes that have demands in electricity. And then you have edges that show direction in which shows the flow of electricity, basically. And so the way you represent electricity across this graph is every node has a specific voltage. And then you have current across the edges. And then you know that the power is the voltage times the current. Okay, and then there are different ways to represent the optimization problem. You could either say that your decision variable are the power and the voltage, or you could say, actually, I don't want the power to be a decision variable. I want the current to be a decision variable, because you know that the power is current times voltage. So essentially, you have a redundancy if they are all decision variables. Okay, and what you want to solve here is to see what's the best value for the voltage, for instance, to be set at these nodes. And the reason this is a bit tricky is that this is alternating current. And because this is alternating current, if in the wall you only add resistance, then if you have an alternating current going through a resistance, what's happening is that you have exactly the same, with different amplitude, but with the same phase. But when you start having capacitance and inductance, what's happening is there is a shift in the sinusoid. And because there is a shift, you actually need to model things. You need to take care about this phase difference between the different nodes. And the way you do that is that you represent the current, the voltage, the power, and so on as complex numbers. Okay, so if you only had resistance, you could only use real numbers, and the way you represent the phase difference is with the angle of the complex numbers. So when you you look at the difference of angle between the complex numbers, that's the difference of phase. You have the fact that the sinusoidal are shifted. And so basically, this means that when you represent a solution, you can actually rotate all the solution. If you rotate the value of all currents, of all voltages and so on by the same angle, it's basically the same solutions. So there is a symmetry in the solution because you only care about the phase difference. So you only care about the difference of angles. And so you need to break this symmetry, but otherwise it's quite appropriate to model this with complex numbers. So we used to not have support for complex numbers in JuMP. And for this kind of application and others, there was a big demand for adding support for complex numbers in JuMP to be able to make these models very easy to write. And we added this recently. And here we are going to use this new feature of JuMP to model this with complex numbers. Okay, so there are some. So this is an actual. This is part of some library of benchmarks. You can find more details if you follow this link. So there are some values, like for the generators, there are bounds on the power generated. So because the power is a complex number, there are two ways to actually represent it. There is the rectangular way when you represent the real part and the imaginary part. But you could also use the polar coordinates and then use, then you have some cosinus and sinus appearing everywhere. So here we are going to use the rectangular way, and P will be the real part of the power, Q will be the imaginary part of the power. And then when you mix the two, we call it S. Okay. And then for the branches, which are the edges of the graph, then each edge is represented by the from node, so which node is coming from and which node it's going to. Okay. I think this is the only information we are going to use from this data. So we do a simplified version. And so from this information, we can build an incidence matrix. In this case, there are as many edges as nodes, so it might be a bit confusing that it's actually square, but it may not be square. So what you have is that on the columns, you have the edges, and on the rows, you have the nodes. So here, what you see is that you have, so here for from, we add 1, and 2, we add -1. So we put a 1 here. For this edge, it's going from this node to this node, so we put a 1 here and a -1 here. It's always the case when you do electricity, you need to have some convention of the signs. You could also have 1 here, -1 here, 1 here, and you should just need to be consistent in which direction you define the current. And yeah, one thing that's still a bit annoying sometimes with JuMP is that we don't support units. And so here, actually, the data has units, but we don't support it. So the way we do this is that we will need to rescale to make sure that we use consistent units, but we don't automatically check units that you could have with, for example, the unit full package. We plan to add support for units in JuMP. So we actually have submitted it as a small development grant proposal to NumFocus. But at the moment, it's not there yet. Okay, so here we use some, let's hide this now. We use some constant here for the, so for the branches, typically, you would expect them to have just a resistance, but here there is also X part, which is kind of the imaginary part of the resistance. Okay, so just think about it that no, everything is a complex number. Okay, and so we now define the impedance, which is just mixes the typical resistance you know about and some reactance part, which is, think about it as the imaginary part of the resistance. And so now we want to model this with JuMP. So it's not going to be linear. It's not going to be convex. So we are going to use IPOpt. IPOpt is a solver in the NLP class. Where is it? Here. Which means that it's okay for him to just not assume much about the problem. It's not just going to ask us when it has a given solution. It's going to ask us, okay, what's the value of the gradient of each constraint, of the gradient of the objective? And it will also ask, what's the value of the Hessian vector product or the full Hessian, so that it's able to do its second order solve. Okay, and so this means that we can basically have the constraints being almost arbitrary. It doesn't have to be linear. Okay. Here, what we want is that the power that we call S, we want it to be a complex number. So what you can do in JuMP is use this in complex plane. And so when you use in complex plane, what you're going to ask is that this is actually a complex number. But most solvers don't actually support complex numbers. And so what we just do is that we create a variable for the real part, a variable for the imaginary part, and then we combine them. And you can see it in the printing. Here you see that we actually just have a real part and an imaginary part, and we just create one variable that so you wanted to name your variable SG1, and what we do is we create a real part that we name real SG1 and an imaginary part that we name imaginary SG1. And that's it. Okay. Now, when we design complex numbers, it was a bit unclear how to deal. So you could specify the bounds with inequality directly here, but you can also define the bounds with keyword arguments. It was a bit unclear to us how you define the lower bounds on a complex number, because of course it makes no sense to say that a complex number is smaller than another one. So we decided to do to still define it. And so, of course, you might not find that it's very rigorous, but we're still doing it. So if you say that this is a lower bound to the complex number, it simply means that the real part is a lower bound to the real part, and the complex part is a lower bound to the complex part. Okay, so component-wise in a sense. But if you don't like it, you don't have to use it. But we're doing it. Okay, so now for the voltages, exactly the same thing. We want the voltage to be a complex number, and here we want to give the starting value for IPOpt. We want IPOpt to start with all the voltages being 1 with 0 imaginary part, because IPOpt is going to do some iterative algorithm. It will need to start somewhere. If you don't give it at a starting point, it's going to decide itself. But here we can make a suggestion and it's going to follow it. And here it's a bit easier. If you give a starting point, which is a complex number, we're going to give the real part a starting point for the real part, imaginary part a starting point for the imaginary part. That violates no law of mathematics. Okay. Now suppose you want to add bounds on the voltage. One thing you, of course, often need to do with complex numbers is to ask for the absolute value, the modulus of the complex number. Of course, if you ask for the absolute value of a complex number, you need to take the squares of real imaginary part, and then you need to take the square root. The issue is if you take the square root, you leave the realm of quadratic expression. So in JuMP, we have 4 categories of expressions. We have variables. We have affine expression, which is a sum of variables multiplied by constant plus a constant. Then we have quadratic expressions. where variables start multiplying each other. And then you have nonlinear expression, which is an expression graph, basically, and that can contain a lot. And so if you were to compute the absolute value, because we need to represent the square root, it cannot be any of these, so it starts being a nonlinear expression. And when you start being a nonlinear expression, when you interact with anything else, it's again going to be a nonlinear expression. So we don't do that. If you take this square root and you square it, we can simplify it to quadratic expression. We don't do that, okay? So it's much better that you directly ask, what I want is the square of the absolute value. And the square of the absolute value, this is a quadratic expression. And so we never build the square root, and we directly do the sum of the two squares, okay? And now you see that you have quadratic expression. Oh. You see that you have quadratic expression here, okay? So when you look at here, you see scalar quadratic function. That's because in math optic interface, which is a solver interface, we're talking about function and expressions, but it's the equivalent to the quadratic expressions. Okay. That's nice. As I told you, there is some symmetry we want to break. So let's say that for the voltage of the first node, there is no imaginary part, and the real part is positive, so that we have basically an angle of 0. That's how you set a 0 angle in a rectangular formulation. And then the objective will be some function of the real part of the power generated at the generators. Okay, we want to, of course, minimize something like this. Now, the last thing we need to add will be the exercise, is we want to add the constraint that the power is the voltage times the current. Okay, and in the real case, you write voltage times the adjoint of the identity. Okay, so what we need to do is that we first need to compute the current, because we don't have a decision variable that is the current. And so for that, we use Kirchhoff's law, and we say, Ohm's law, sorry, and we say that is the difference of voltage divided by the impedance. But that's the current at each branch. And then if you want to know at each node, here you have the current at the node. So the current, what we mean by that is going to be the sum of the current arriving minus the sum of the current leaving. Okay. And actually for this, you can also, to solve these two problems, you can use the incidence matrix that we built above. Actually, because it's already 47, you don't have a lot of time to do the exercise. So if this is the recording, you can maybe pause and do the exercise. But here, live, I'm not going to give you any time, sorry. So, okay, how do we do this? We are going to take the difference. So at every branch, we want to take the difference of the voltages. And that can be done by transpose of this B matrix times the vector of voltages. Okay, then we have the difference of voltages. Then to get the current for all the branches, we divide by the impedance. It's fine. And then we multiply by B. This is a bit less intuitive, but what this is going to do. So we have the current at every branch. If we multiply the current at every branch, it's going to do +1 for here for the from node and -1 from the to nodes. And so if the signs are correct, this is correct. Because you always have 50% chance that you did the signs right. And so you can just multiply by the B matrix, and now you have the sum of the currents going in and out at the node. I know you can just say that, okay, the total power should be the voltage times the conjugate of the currents. Okay, that's one way to do this. But actually, so now you can optimize, and you always, of course, need to check that it's correct. You can also say assert is solved and feasible, and this one, there is solved and feasible that returns a bool. But if you want to save time and not have if not is solved and feasible, then throw some error, you can write direct assert is solved and feasible, and this is already going to throw if it's not solved and feasible. So this is now 1 line instead of 3 lines. And now, solution summary. What is the solution? No, this is not optimal anymore. This is locally solved. And the reason is that because this formulation is not convex, IPOP doesn't check for convexity, so it's never going to say it's optimal. IPOP is just going to say, I found a local minimum. I have no idea if this is the global minimum or not. Because if you know the problem is convex, then you know a local minimum is global. But IPOP doesn't do any convexity checking or anything, and here I don't think it's convex. So it's just going to tell you it's a local minimum. But if you're happy with that, then it solves your problem the way you want it. And you can ask for what's the objective value. Okay, so in a sense, it has feasible primal and dual solution. Okay, so the last thing I wanted to talk about is performance consideration. Okay, we have a lot of questions about, oh, suddenly I realized that if I'm doing a profiling, actually building my JuMP model is slower than solving it. Okay, and of course, this makes no sense. In a sense, JuMP is doing the easy part, just taking your model and giving it to the solver, and the solver is doing all the hard work. So of course, we don't want this to happen. We always want that the time taken by JuMP is completely negligible. But when you give a complete, very simple, user-friendly algebraic way to build the model, it's very difficult to prevent the users from writing a slow code. Okay, so we're catching many cases, but you can still write a code that's going to build your model slow, because in a sense, JuMP is part of Julia, and so you can write any Julia code. We cannot prevent you to write something that's going to be slow. Okay, so if you see that you have a performance issue, it's important to know a few internal details about JuMP. And so something that's very nice about Julia is you can always ask what is the method being called by a given function. So here, if you multiply the B, which is a sparse matrix, by a vector of variables, V, actually V, they're complex variables, so they're actually already affine expressions. And you can see that this is actually not going into sparse arrays, as you would expect, because normally in sparse arrays, you define the product of a sparse matrix with a vector. But actually, what's happening is that the way we represent expression, either affine, quadratic, or nonlinear, is with a structure that's heap allocated. And so when you add to a affine expression, and you need to create a new affine expression to contain the result, well, this takes time because you need to allocate a new affine expression, copy everything. But if you think about it, if you add to a affine expression, what you could do is take the first one, for example, and modify it and just append to it all the terms of the second one, right? But of course, we cannot do that. Like in base, the plus function doesn't say that it's going to modify the first argument. Okay, so when in sparse arrays call plus between two JuMP affine expression, we don't know. When in JuMP we need to implement plus between two affine expression, we don't know whether we are allowed to modify the first argument or not. Maybe the first argument is actually something created by sparse arrays, and it's actually fine because it's some accumulator, but we don't know that. Even if when you write plus equal, you just receive plus at the end. So what we ended up doing is redefined many functions of sparse arrays of linear algebra and re-implement them. Of course, you start a bit with a copy paste, but then you need to actually modify quite a lot so that you this is my somewhere in my computer. So you need to modify the code so that instead of plus, you say I do a plus that mutates the first argument. Okay. And if we didn't do that, then the performance of this would be horrible. Here it's okay because the sparse matrix doesn't have a lot of entries. But if you do the classical matrix vector product of Julia, the generic implementation and not the modified implementation of mutable arithmetics, the performance is horrible. Okay. So whenever you do something like that, it's important to check that this is going through the right route. And if you do some profiling, you can check if you see that this is executing some generic implementation in linear algebra or sparse arrays. This is a big red flag, because in mutable arithmetics, we try to catch most of the calls with multiple dispatch, but we cannot catch every use case. It's a bit unmaintainable. So until in linear algebra and sparse arrays, they may be defined at some point some mutable arithmetics interface and use them directly. That will be the right fix. At the moment, we need to somehow catch the slow case and re-implement them. Okay. And so normally, okay, the performance should be okay, but still it's way slower than if you actually do matrix vector product with a matrix of floating point numbers and a vector of floating point numbers. So anytime you start interacting with JuMP expression, everything will be much slower. So if you think about it, I think it was almost low. If you think about it, here you multiply with the first matrix, with the second matrix, and with the third matrix. So you're doing matrix vector product, 3 matrix vector product. And of course, you all know that you could also write like first do matrix product and then do 1 matrix vector product, but you all know that this is silly. Of course, if you need to multiply 3 matrices and then a vector, you always want to do 3 matrix vector product and not matrix product and then at the end doing the matrix vector product. You all know that. But actually in this case, because the vector contains JuMP expressions, this is actually going to be faster to do this. Because here, now this contains a vector of JuMP affine expression. And so here we need to deal with JuMP affine expression. And here again, it's a vector or JuMP affine expression. So even if it's 3 matrix vector product, it's matrix vector product using JuMP expressions, which is much slower than just normal numbers. And here, this is matrix product, but between floating point numbers, so much faster. Okay, so of course, this is just in a sense, maybe a fixed cost. So you need to think about maybe at some point, the complexity of this will be so horrible that it's still faster to start interacting with the JuMP expressions. But in addition to the complexity consideration of this operation, you need to think about the fact that when you manipulate JuMP expressions, these are not just first, every time there might be some heap allocation, and also the JuMP expression, if it contains 1000 terms, well, it's not O of 1 to do a multiplication, right? So all these things need to be taken into account. In that case, the difference of performance is not that bad, but still the matrix product is actually faster. And if you try larger example, you see there is a difference of 2 between the two. And actually, you can also try a dense case. In the dense case, you would really think like matrix product will of course be slower than the matrix vector product. But actually, if you look at it, the matrix vector product is like 7.5 times slower, more like 10 times slower if you look at the mean. And the reason for this, like here you would think, okay, but here the complexity is on my side. Like this is going to be n cube complexity. And this is like n square and then again n square. So n square plus n square is smaller than n cube here. But the thing is that because here you're building a vector affine expression where each affine expression contains n terms, this product will still be n cube. It's not going to be n square in complexity. Okay. So this is the kind of course, start writing your model without worrying about these things. But if you start seeing performance issues, start looking at this from this angle. And then you will be able to make your code much faster. And at the end, it should always be that the model generation will always be negligible compared to the solve time. Always. If you write the solver the right way, there is no way you cannot achieve that, especially because Julia is a compiled language. But it may happen that at the beginning, the way you write your code might be slow, and you need to take a look at these things. Okay, that's all for the tutorial. Thank you all for.
Thank you very much. I may have one actually related to what you just said.
Yes.
I know that JuMP is a very powerful tool when you want to model your problem and then solve. Because I teach and I'm professor in combinatorial optimization, so I use JuMP for modeling and solving, right?
Yes.
But then I'm wondering if I want to start to develop like decomposition methods.
Yes.
And that means, for example, a branch and price or a column generation. That means I'm going to solve many times models that I will need to update. So the question is, should I use JuMP as an interface? At some point, there will be an overhead cost, right? Especially if the method is designed to solve multiple times a model that is supposed to evolve depending on the solution from the previous iteration. So
yeah, it's a very good question. So for example, LP solvers, they are fast at solving the problem, but they're also extremely fast as if they solve the problem and you just add one more constraints and then say resolve, they can be extremely quick about it. And so if you create the problem from scratch every time, you create the problem from scratch, you solve the first time, then JuMP would be negligible. But maybe if you create it from scratch again with the new constraint and solve again, because the first, the LP, we need to start from scratch again. And that's very inefficient. And second, compared to the solve time of the LP of just one more constraint, then here, the building part might start to be noticeable. And so in JuMP, if you add a constraint, you can always add constraint or variable after after you have optimized. And then we are just going to add them to the solver. And if you optimize again, then it depends on the solver what happened. So some solver will say, oh, I don't support adding a new constraints. So we're just going to reset these solvers, empty their model. And then when you ask to optimize again, we're going to give them the new model. But this solver that support adding new constraints, then we are going to keep them completely in memory untouched, just add the constraints. And when you resolve, we ask them to resolve. So it's going to be transparent to the user in a sense. If the solver is going to be reset or not, we are not going to throw warnings or things like that. But you can inspect if you want. You can see after you add the constraint, you can check if the solver has been reset or not. Okay. But the solver that can do this efficiently will do this efficiently.
Thank you.
Yes. Yeah, and a very good package for that is this one. In this package, we want to make this workflow very easy. And so what you do is you say, this is a parameter. And here it's even better than just adding the constraint. What this is going to happen is that if you solve, then you change the value of the parameter and you resolve, it will see, oh, I don't need to add constraint. What I need to do is modify the constraint. But some solver supports saying, I want to just modify this coefficient in these constraints. Okay. And even some prefer if you do this with a bunch of constraints at that time and not and give a bunch of change in once, in bulk. And this package makes it easy to do this very efficiently. So this is a very important use case of JuMP that we try to make it easy and efficient.